So for a 3 by 3 matrix, um, we've got 3 rows, 3 columns, and so you can see it's not as simple as just crisscross and then you're done. So I'm going to show you that there's actually 2 methods to finding the determinant of a 3 by 3 matrix that we would do without just typing it in the calculator, and then I will show you with the calculator the third method where we just type it in and use the calculator to calculate the determinant. So first things first, the one method is it's kind of an interesting method. You sort of cheat. You take your first 2 columns and you copy them over. Like so. And then we're going to multiply along the diagonals. We're going to do A times E times I B times F times G and C times D times H. Those are all the positive ones. Then you start at the bottom and go up. These are all the negative ones. G times E times C, it's a minus GEC. HFA and IDB. And then you would combine these 6 numbers together, and that would give you your determinant of your 3 by 3 matrix. So that is that's the diagonals method. It's nice because it's very much it's very similar to the 2 by 2 matrix because it's just multiplying along diagonals, and it is fairly straightforward. When you multiply them all out, you see that you'll come up with a if these are all numbers, you'll come up with a scalar quantity again called the determinant of that 3 by 3. There's another method called not called oops, I just clicked the wrong thing there. Reduction along the minors. Oh, come on. So in reduction by minors, the matrix gets turned into three other matrices that are 2 by 2s. And so here's what we're gonna do. Guys, this is R1, R2, R3, C1, C2, C3. So what I'm going to do is if this is if the letter A here is in the position 1, 1. So if you take 1 plus 1, you get an even number 2, obviously. So that's important because each minor has a coefficient in front of it. And whether the coefficient is a positive or negative depends on the sum of the 2 positions numbers. So 1, 1 is even, so it has a positive coefficient. Whereas the B is in row 1, column 2. So if you take the 1 plus the 2, you get 3. So the B will have a negative coefficient. And C is obviously in the row 1, column 3. So that's another even number, so that would be positive. So that's when we get into this reduction by minors, that's how I'm going to know whether or not the coefficient is positive or negative. is by looking at the sum of the two position numbers. So a minor is simply if you take the whatever element you want, and in this case, I'm going to start with the A, and I'm going to cross out the row and the column that A is in. And if you look over here, oops, if you look right here, you see a 2 by 2 matrix. So the minor for this case, for A, is the 2 by 2 E, F, H, and I, like so. Now, I'm going to move along the top row. So my next minor, hang on, let's see if I can get that, there we go. I'm going to go to the B. Come on. Now, remember I mentioned earlier that B would have a negative coefficient because it's row 1, column 2. 1 plus 2 is 3, so I know it's negative coefficient. The minor for B is a little tougher because you can see it's split around the line here. But there's the minor for the element B. So it's D, F, G, and I, like so. And then my last minor, you can probably already imagine what I'm going to do is move and figure out what the minor looks like for C. Okay, well, C is in row 1, column 3. That's even, right? 1 plus 3. So I know it's going to be a positive C, and you can see, you can look over at the matrix and you get the minor for C is D, E, G, and H. So now what we're going to do is we're going to evaluate each of these 2 by 2 determinants, okay, which, as you remember, if I go back a page here, right here, the 2 by 2 minor reduction is here. It's just this diagonal going from upper left to lower right minus the one that goes from lower left to upper right. So we do have ourselves an easy way to find a 2 by 2. So that's all I'm going to do here is E times I minus H times F. That's an E. There we go. And I've got D times I minus G times F. And I've got D times H minus G times E. And sure enough, if you distribute each of those coefficients, you get A, E, oops. Uh-oh. Whoa. My computer just did something weird right there. AEI minus AHF minus BDI plus BGF plus CDH minus CGE. And pretty much, except for the order, you can see that those are the same terms that we got up there. And so, once again, Diagonals method, reduction along minors, doesn't matter which one you choose. I leave it up to you if you want to work it out. It doesn't matter to me. The reduction by minors method is nice because it relies just on the 2 by 2 matrices. You have to be able to keep track of whether it's positive or negative. And notice I used the top row, but you don't have to use the top row. Let me just do it real quick over here. Oh man, that's terrible. Try this again. Still terrible. Okay. Because remember, this is row 1, row 2, row 3, column 1, column 2, column 3. And let's this time, let's do a different minor. Let's do the middle row minors. Why not? So I'm going to, oh, what color? Orange, sure. I'm going to do this row. And so I'm going to start out with the first minor, which is the minor for D. Now remember, since D is in row 2, column 1, you take the 2 plus the 1, that's 3. That's a 3. That's odd. So my first minor now is going to have a negative coefficient, like so, negative D. And then I'll put in its minor, which would be B, C, H, and I. Then I'll move to my next minor, which would be for E. Now, for E, guys, E is in row 2, column 2, so 2 plus 2 is 4. E is going to have a positive coefficient, positive E, and my minor is A, C, G, and I. And then F has a negative because it's in row 2, column 3. 2 plus 3 is 5. So I have negative F times the minor A, B, G, H. And that's how I can would reduce this by minors if I wanted to use the middle row. It doesn't matter which row you choose. Most of the time I just take the top row just because it's on top, but it certainly is not, it's not required to be any one of the rows. You can expand down a column if you want. Just remember that you take the row number and column number, add them together, and if it's even, the coefficient's positive. If it's odd, the coefficient's negative. So that is how we find the determinant of a matrix, which was a lot to set up. We haven't even talked about the cross product yet, and we're already like 27 minutes into this. So I am going to pause the recording right here so that if people have some questions they want to ask, they will be able to ask them verbally, and then we'll come back in just a minute. So let me pause and go. So now we're ready for the big goal of the day, is